Okay, now we are moving right along to part C. This is the final part of the January 2020 exam. In my opinion, these tend to be the hardest questions on the exam. If you can answer these questions, boy oh boy, are you in good shape. Okay, so let's look. So we first have 4 questions that go with the same sample of writing. Compare the chemical reactivities of nitrogen gas and argon gas based on Sir Ramsay's experiment using magnesium. So now I do have to go up here and read it. Sir William Ramsay is one scientist credited with identifying the noble gas argon. Sir Ramsay separated nitrogen gas from the air and reacted it with an excess of magnesium, producing solid magnesium nitride. However, a small sample of an unreactive gas remained with a density different from the density of the nitrogen gas. Sir Ramsay identified the unreactive gas as argon and later went on to discover neon, krypton, and xenon. So, compare the chemical reactivities of nitrogen gas and argon gas. In the experiment, nitrogen gas reacted, but argon did not. Nitrogen is more reactive than argon. Okay, there we go. Next one, we have another long one. I have 2 long ones and a few in a row. Compare the density of nitrogen gas to the density of argon gas when they're at 298 Kelvin and 101.3 kPa. The question mentions nothing, which means probably what? Can you guess? Yes, I need a reference table. So I need to go to the reference table. I have a density column. The density of nitrogen is this, and the density of argon is this. Okay, so which is greater? You have to be careful. This is 0.0011. Argon 0.0016. Oh, argon is more dense. Okay. Argon gas has a greater density than nitrogen gas. Okay, let's move on. State in terms of, okay, my answer has to literally have these words, right? State in terms of valence electrons why the noble gases that Sir Ramsay discovered have similar chemical properties. Well, he discovered argon, neon, krypton, and xenon. Why do they have similar chemical properties? Well, let's look. Neon, 8 valence electrons. Argon, krypton, xenon. Okay, so the gases discovered all have 8 valence electrons, which you remember, this is a stable octet, right? Okay. All right, next one. State the trend at standard pressure of the boiling points of these noble gases as they are considered in order of increasing atomic number. So I need the boiling point of argon, neon, krypton, xenon. So let's look. In order of increasing atomic number, it is neon, argon, krypton, xenon. How do I find their boiling points? Well, I just look it up. Don't make it harder for yourself. So boiling point of neon, 27. Boiling point of argon, 87. Boiling point of krypton, 120. And boiling point of xenon, which I gotta go really far down here to see, 165. So what is the trend? Okay, well the trend is that as the atomic number increases, the boiling point increases. Okay, you just had to be careful to consider them in the correct order. There we go. All right, look, 70 and 71 are going to have short answers. 72, we're back to a little longer. So those questions are down here. All right, so let's not do the reading. Let's go to the question first. State how many times greater the hydronium ion concentration in the lake water is than the hydronium ion concentration in the sample of normal rainwater. Okay, so this is a lot of information here. So first of all, what is a hydronium ion? So let's look it up in case you forgot. Hydronium ion is first right here. Hydronium ion is H3O+. And a hydronium ion is basically an H+ that has stuck to a water molecule. So what this does is indicates acids. And when we're looking at a pH scale, right, from 0 to 14, 7 being neutral, okay, this is acid on this side, base on this side. As we move this way, the concentration of H+ goes up, or H3O+. So that means a pH of 10 has less H3O+ than a pH of 2. All right, so now we have to compare. We're comparing, say, how many times greater the hydronium ion in the lake water versus rainwater. All right, so it says the hydronium ion is greater in lake water, right? So what is the pH of normal rainwater? 5.6. Okay. And what is the pH of the lake water? 4.6. Okay. So remember it told me there's more hydroniums here. So this has more H3O+. Why does it have more H3O+? Because it is more acidic. So what is the difference between these two pHs? Well, it's a difference of 1. But that is not how many times the H3O+ is different. So let's just look at a fraction of a pH scale. So if we have 4, 5, 6, 7. Every time the pH changes by one number, the concentration of H+ changes times 10. So this would be a 10-time decrease in H3O+. This would be a 10-time increase in H3O+. So I moved one pH value, so the concentration changed times 10. Right, 10 times 10. Okay. State the color of methyl orange in a sample of normal rainwater. Okay, there's the pH of normal rainwater. Let's go to the indicators. All right, right here. Oops. So here are my indicators. I'm looking at methyl orange, right? And normal rainwater is 5.6. I'm just going to write it right here so I can see it at the same time. I'm looking up methyl orange. What color would it be at 5.6? Well, here's methyl orange. What does this color range mean? That means that below 3.1, methyl orange is always red, and above 4.4, methyl orange is always yellow. In between this range, I'm like, I don't know. But so I'm not going to be asked in between the range. So at 5.6, well, 5.6 is greater than 4.4. So on this short line, I'm going to write yellow. All right, and 72, one more question for this section. Based on table G, describe what happens to the solubility of SO2 gas as the temperature increases from 10 to 30 degrees Celsius at standard pressure. So if you don't go to table G, come on, what are you doing? So here's table G, here's SO2, temperature change from 10 to 30. So here's SO2 as the temperature changes from 10 to 30. See what's happening to the line? So what's happening to the solubility? The solubility decreases. Oops, the solubility of SO2 decreases as the temperature increases from 10 degrees Celsius to 30 degrees Celsius. Okay? All right, we are moving right along. Let's turn our page. Ooh, look at this. I got a diagram. I got an equation. All right, let's see. All right, oh, this is 5 questions for the same content. All right, let's see what we got here. Write the empirical formula for acetylene. All right, so let's go up here. Here is the molecular formula for acetylene. So how do I write the empirical? Well, empirical is the reduced chemical formula. It's in lowest terms. So if it's C2H2, that's what I started with. I'm going to divide this number by 2 and divide this number by 2. That will give me C1H1. But I don't write the ones, so just CH. Okay? CH. That's it. 74. In your answer booklet, use the key to draw a particle model diagram to represent the phase of O2 gas. Your response must include at least 6 molecules. Well, I'm drawing O2. So O2 is a diatomic molecule, so that means I have 2 particles of oxygen connected to each other. So I could use open circles if I wanted to use closed circles. Would I be right? I don't know. Let's look. I would not. Look at this. This says this is an oxygen molecule. So they already gave me a hint. I didn't even have to know that. All I get to do is draw 6. What would it look like as a gas? Well, if it's a gas, they're spread far apart. So I just have to draw 6 of them spread far apart. 1, 2, 3, 4, 5, 6. Perfect. All right, now it says balance the equation in your answer booklet for the reaction of acetylene and oxygen using the smallest whole number coefficients. Okay, so it's this equation right here that I have to balance. So let's try. Usually they don't give us such a hard one, so let's try. Let's start with carbon. I have 2 carbons here, and I only have 1 carbon here. All right, so I fix it by writing a 2. That gives me 4 oxygens, which I could easily fix, but now look over here. Ugh, it's always got to be something complicated, because you see, I only have 2 H's here. So 2 H's here, that's perfect, but this is an odd number of oxygens. So you know what I'm going to do? Say, okay, scratch this. I'm going to put a 2 right here. Trust me when I say sometimes putting a 2 in front of the thing that you're burning or the most complicated looking formula can help to figure things out. So let's see if it does. This is 2 times 2 is 4 C's. So let's make this be 4 C's. Okay. 2 times 2 is 4 hydrogens. So let's make this be 4 hydrogens. 2 times 2. All right, now oxygen. Oxygen's by itself here. So as long as it's a multiple of 2, I can balance it easy peasy. This is 4 times 2. That's 8 oxygens. 2 times 1 is 2 oxygens. So I have 10 total oxygens, but remember I have the subscript of 2, so I would put a 5. 5 times 2 is 10. And there we go. That's balanced. So I'm just going to make sure I cross that out clearly so you could see my answer. I don't need those. 76, short line. Determine the mass of 25 moles of acetylene, and it gives me the gram formula mass. So I need a formula, and I'm going to use this one. Moles equals given mass over gram formula mass. Okay. So moles equals mass over GFM. Determine the mass of 25 moles. So I have 25 moles equals mass is what I'm trying to find, divided by the gram formula mass, which it says is 26. Okay, so what am I going to do? Put this over 1. Cross multiply. So mass is going to be simply 25 times 26. 25 times 26 equals 650. And here we go, 650. All right, so we're done with this section. Let's move on. And we are right here. And we have, again, 5 questions in this section. All right. Let's go here. Compare the, so we may need to read this, we may not. So let's just go to the questions. Compare the thermal energy of a 10 gram sample of water at 25 degrees Celsius to the thermal energy of a 1,000 gram sample of water at 25 degrees Celsius. Well, they have the same temperature, same substance. What's different? The mass. If I have more mass, I'm going to have more thermal energy. So the 1,000 gram sample has more thermal energy. Oh, wait, hold on. I missed a question. 77. Let's write our answer for 78 anyway. So the 1,000 gram sample has more thermal energy. Okay, but somehow, oops, I missed this question. So let's go back. I guess I was over the mole reaction. Okay, explain in terms of bonding why the hydrocarbon gas used in the cutting torch is classified as an alkyne. Okay. So here it's acetylene, that's this. What makes something an alkyne? Well, if you don't remember, you go to the reference table, right? Just here. What makes something an alkyne? In terms of bonding, it has a triple bond between 2 carbons. It's an alkyne because it has a triple bond between 2 carbons. That's why it's an alkyne, right? Okay, now we go back. I apologize, sorry about that. So we answered 78, now let's look at 79. State what happens to the potential energy of the molecules in a solid sample of hexane at negative 90 degrees Celsius as heat is added until the hexane is completely melted. Okay, well, solid, now we're melting it, right? The kinetic energy isn't changing, right? The temperature isn't changing, but the potential energy is changing, and we're heating it, so that means the potential energy is increasing as it is heated. Okay, the potential energy is increasing. All right, ooh, our last page. All right, but we're right here. Determine the vapor pressure of water at 69 degrees Celsius. How do we determine it? Well, if it's not in the question, where is it going to be? In the reference table, especially if it's just a number. Okay, so I am going to look at water 69 degrees Celsius. So 50, 55, 60, 65, 70. So just right in front of this line, here's water's line, right? And so I'm going to go up right here, right there, and go across. It's right about here, a little bit below this line. And this is 10, 20, 30, 40, 50. So it's a little bit under 30. So you could say 28 or 29. I'm going to say 28. Okay, 29, also okay. All right, let's look at 881. Explain in terms of the molecular polarity why hexane is nearly insoluble in water. So I got to talk about polarity. Okay. Water is polar, so we should know that. And it says hexane is insoluble. Hexane is insoluble in water. It literally gave me that, right? So it must be non-polar. Because if it was polar, it would dissolve in water. If it was ionic, it would dissolve in water. All right, now we're on to 82. Explain in terms of molecular formulas and structural formulas why 2,2-dimethylbutane is an isomer of hexane. So I could draw it, so let's draw butane. But is 4. 2,2-dimethyl means I have a methyl group on carbon number 2. All right, so how many total carbons do I have? I have 6, just like if I had hexane. So I have to talk about molecular formula and structural formula. This is truly just a definition question. And I could say they are isomers because they have the same molecular formula but different structural formula. How do I know they have a different structural formula? They have a different name. So a different name always indicates a different structural formula, even if it was just the address. So if it was 2,3-dimethyl butane, these two would be isomers. Different name, different structure, okay? And if they have the same molecular formula, that would make them isomers. All right, we're on our last section. Oh my goodness. Whew, it's an electrochemical cell. All right, here we go. We can do this. A lot of reading. Let's skip it. Let's go to the questions. State the change in oxidation number that occurs for oxygen in the overall reaction. So let's focus on the overall reaction. State the change in oxidation number that occurs for oxygen. You could see my answer book says from blank to blank. Okay. So on this side, oxygen is in a compound. On this side, it's alone. When it's alone, its oxidation number is 0. And in a compound, let's look at the periodic table. In case you forgot, oxygen should be one that you remember, but it is -2. All right, so oxygen goes from -2 to 0. All right, 84. Compare the number of electrons lost by oxygen to the number of electrons gained by hydrogen in the overall reaction. Well, if this is redox, okay, you must remember this. The number of electrons gained is equal to the number of electrons lost. Okay, that's just the way it is. Last one, little answer, we probably had to do a calculation. Determine the number of moles of hydrogen gas produced when 0.0004 moles of oxygen gas is produced in the cell by the overall reaction. All right, so we have to use this. So let's write what we have to start with. 0.0004 moles of oxygen gas. But I don't want moles of oxygen gas, I want moles of hydrogen gas. So I'm going to do this. And I want to get rid of this because I don't want this, so throw it in the basement, right? That's where things go to get rid of. Moles of O2. I want moles of H2. So how can I convert moles of O2 to moles of H2? I use the balanced equation, and I look at the coefficients, not the subscripts. What's the coefficient in front of oxygen? Well, that is 1. What is the coefficient in front of hydrogen? Well, that is 2. This will cancel out. So all I need to do is take this number and multiply it by 2, since the bottom numbers are both 1. And that is obviously, hopefully you can realize this, give me this. All right? And then I'm going to put that answer right here, 0.0008. And there we go. Whew. Oh my goodness, we finished the whole thing. We did the whole exam. That is the end of the January 2020 exam. And I hope this helped you out.